Hi, everyone. So this is just going to be a short lecture. So if you notice on the syllabus, I did have it written down that we'd be covering the beginning of chapter 17, but we did have our quiz today, so I didn't want to overwhelm people. So we took our quiz. I'll get that graded just over the weekend. We'll go through this video, get caught up. The way I'm kind of doing this, it's a little bit out of order in terms of the sections in which they appear in the book. I think this order that we're going to talk about it provides a little bit more flow. So what we're going to focus on today is going to be just two topics, the common ion effect and then buffers as well. And I'll introduce one new equation, the Henderson-Hasselbalch equation, and then we'll do two representative examples of that. So we'll notice that chapter 17 dovetails into chapter 16, just kind of like how 16 dovetailed in from chapter 15. So what is the common ion effect? So I'll read through the definition first, like we usually do, and then what I want to do is give you more of a concrete example to help put into perspective what the definition is actually trying to say, right? So the common ion effect. We're looking at the shift in the position of an equilibrium. So it means we've already established an equilibrium, and now we're going to stress the system. We're going to perturb it somehow. So it's either going to shift to the left or to the right. And that's what we're going to be looking at, right? So we're looking at the shift in the position of equilibrium, specifically upon the addition of a substance that provides an ion in common with one of the ions already involved in equilibrium. So what I have down here as a representative example is the weak acid acetic acid. When it's added to water, it's going to set up an equilibrium where it forms hydronium and then acetate, right? So once an equilibrium has been achieved, there's going to be some protonated acetic acid, there's going to be some hydronium, and there'll be some acetate. And we know from chapter 15 is that once a system has reached equilibrium, as long as we don't perturb it, it will stay in that equilibrium forever. So how are we going to stress this system? For this particular example, we're going to be adding a ion that's in common with one of the ions that are already in equilibrium. That's where we're getting that phrasing, common ion, then effect is just, some sort of effect. So imagine I have this solution of acetic acid, and then I dissolve into it this compound here. So this is sodium acetate. Sodium acetate, you've actually probably eaten before. It's the flavor of vinegar in salt and vinegar chips. I would not recommend pulling it off the shelf and licking it, but this is the compound that is responsible for the vinegar flavor. So if I take that compound, sodium acetate, and pull it off the shelf, and then I dissolve it into the same solution that the acetic acid was in, so I'll use that arrow to say, look, they're both in the same water, right? So I'm dissolving that sodium acetate into solution. It's an ionic compound, and it's going to dissociate into a sodium cation as well as an acetate anion. And so this is the idea of the common ion effect. So I've added literally two things to this solution. I added acetic acid and sodium acetate. What I see here is that if both are dissolved in the same sample, acetate is shared by both of these compounds. What that's going to mean is that I can actually artificially increase the concentration of acetate by just dissolving sodium acetate into solution. For the most part, if we don't have a common ion, like if you see here, sodium plus doesn't appear in the top reaction at all. It just kind of floats around to make sure all of our charges balance out. So if that was a little quick, what I want to do is just do a quick or a more concrete quantitative example. So again, we'll take our acetic acid example, but now we're going to apply some numbers to it, right? So it says the Ka of a 0.10 molar solution of acetic acid is that number. It says calculate the pH of a solution that is prepared by dissolving 0.1 mole of acetic acid and 0.1 mole of sodium acetate in enough water to make a 1 liter solution. That's a lot of information at once, right? But let's, again, fall back to the skills that we have. Forget the sodium acetate right now, right? if I'd write out the balanced chemical equation for the dissociation of acetic acid, if I'm saying forget this just for now, we're going to say we dissolved 0.10 moles of acetic acid in 1 liter. Well, moles per liter is molar, so we're at a 0.10 molar solution, right? We said we don't care about water, approximately 0. And right, I'm saying we're pretending like this hasn't happened yet, so I'm going to put down 0 for the acetate. So that's nothing different than we've ever done in chapter 16. We'd set up our ice table, we could use our Ka, would figure out what X is, the concentration of hydronium, plug it into the pH equation and get the pH. So all we're going to be doing is adding just not even another step, just a little bit more information. We're saying that, yeah, I started with a 0.1 molar solution of acetic acid, but the information also says I've added 0.1 mole of sodium acetate, and it's also in the same 1 liter solution, so that concentration will also be 0.1 molar. So here we can start to see, instead of having where we have just our concentration of acid on one side, and then everything in chapter 16, we had 0 on the other side, right? We're actually having that common ion is there. And so this becomes a little bit more challenging now. So how do I know which direction the equilibrium is going to lie, right? Is it going to, given my starting amount, right? Maybe it's in equilibrium, right? We could figure that out by calculating Q and comparing it to Ka, right? Or what we can do is take a look at how big the Ka is, right? This Ka, right, that's a weak acid. And so actually, if we compare that to the Kb, I don't have the number right now, but if you did, right, and we also can calculate the Kb using Ka times Kb equals Kw, we'd find out that Kb is much weaker than the Ka. That's telling me the acid is probably going to push in this direction, right? And a lot of this is going to come down to, determining, is the Ka bigger than the Kb? So what we could do is set up our table, right? We have our 0.10 molar. We don't care about water. Approximately 0 molar for hydronium. And then we said we had our 0.1 molar for the acetate. The acid is stronger than the conjugate base, so it's going to move from left to right. So nothing really has changed in terms of our change row. And so at equilibrium, really nothing too much different, except for this last piece here, right? So we started with 0.1 molar of the acetate, but now we've perturbed the equilibrium. Which direction is it going to go, right? Is it going to go all the way to the left, or is it going to go to the left, to the right? Well, we need to figure that out. We can write down our Ka expression. And if I plug in my equilibrium values, I end up with, sorry, I got something in my throat. Right? We have a concentration of our products over the equilibrium concentration of our reactants. So on this one, and I'm going to have some of the math on the next slide, we're seeing it's becoming a little bit more complicated. I haven't done it out the long way. I do not know if the quadratic equation is going to work for that one. Occasionally, you get into some really higher polynomials. So like when you have x to the third, x to the fourth, it becomes very, very difficult to solve after that. And it takes some higher level math. So what we're going to need to fall back on is going to be our assumptions. For this, we're comparing x to the value of 0.1. My assumption is that x is a lot smaller than 0.10. How can I write that mathematically? It's saying that if I took the 0.1, I subtract x from it, it's going to be approximately 0.1 within significant figures. What does that do if my assumption holds? Well, that means the x's are so small, effectively my concentration is unchanged for both, and I get a simplified expression here. Solve for x. Now it's actually, there's no square roots or anything. It's just a really simple algebra problem. I've already gone ahead and checked the assumption. You can do that yourself. I'm trying to keep it clean, but if you definitely take the 0.10 and you subtract 0.1234 from that, it is going to be approximately 0.10 to two significant figures. So our assumption does check out. Then at that point, I just need to plug it into my equation, and we end up with our final pH. If we compared this to just pure acetic acid at the same concentration, the pH will actually be a little bit lower. By adding in the conjugate base, even though it's a common ion, it's actually increasing the pH very slightly. So effectively, this is a new way of interpreting, not a new way, but it's an additional way of looking at Le Chatelier's principle, right? So the addition of acetate, right, acetate, to a solution of acetic acid, it's suppressing the dissociation of the acid because we're already loaded up on this side. And so the equilibrium is going to shift towards the left. Yeah, the acid dissociates, but it's not going to dissociate as much. So we can phrase it as it's moving back toward the left a little. So it's not dissociating as much as it would if there was not sodium acetate dissolved. And so this will bring us to the idea of a buffered solution. So a buffer solution, if you might have even heard the term before, not in a chemistry sense, it just means a system that's resistant to change. And when we talk about buffered solutions in chemistry, we're talking about it's a resistance to the change in pH. So the definition of a buffered solution, a solution which contains a weak acid and its conjugate base, and it resists drastic changes in pH. So we'll get to the idea of drastic changes in pH in a second, but when we're looking at a buffered solution, right, we would have the weak acid, in this case acetic acid, and then in blue you have the conjugate bases. So we could have an acetate buffer. HF, you can have a hydrogen fluoride buffer, an ammonium buffer, and a phosphate buffer. And there's many, many, many more than this. But minimum, you have to have the weak acid and its conjugate base. So let's see why they resist changes in pH, right? So a buffer solution is going to have a good amount of the weak acid and roughly equal amounts thereabouts of the conjugate base. So the example we have on the top is I have my acetic acid. Acetate is its conjugate base. Where is it coming from? Probably sodium acetate, like we used in a couple other examples. So what we care about is this, right? And it's saying I have a good amount of weak acid and a good amount of conjugate base. So if you had a pure water solution and added a small amount of like sodium hydroxide, we'll actually find out the pH is rapidly and massively changed usually. So we've seen it for even like 0.1 molar solutions of acid are pretty acidic. So adding even a small amount of acid or a small amount of a strong base can greatly affect the pH of pure water. However, buffered solutions are going to resist those changes in pH. Why? Let's take a look. If I added, say, a small amount of OH, so we said if you added it to water, the pH goes through the roof, and it's like pH, 12 or whatever. I'm making that up, but it would go up. However, if I add a small amount of the strong base to a buffered solution, well, there's some amount of acetic acid hanging around. What do we end up getting? We actually get a high school reaction. All it is a neutralization reaction. The hydroxide will pull off that H, that acidic proton that's on the acetic acid, will form our conjugate base in water, right? So if we look here, because that strong base is so reactive, it's going to pull the reaction all the way to the right. It's a very strong base, really strong. If we look at something like a strong acid, they're going to pull everything to the right really hard. What that means then is effectively what I started with as a weak acid and a strong base has now been converted to pure water, which won't affect the pH, and then a weak base. So the pH is going to be affected a little bit, but instead of having a strong base affect the pH, Actually, the weak base is just going to affect the pH, and it's only going to increase the pH by a small amount. So we're going to call that resisting the change in pH. We can apply the same logic. So you have the same buffered system, but now imagine instead of adding hydroxide, I'll add hydronium to it. Maybe it's HCl or nitric acid, something that's very strong. A small amount of nitric acid or a small amount of hydrochloric acid added to pure water will greatly drop the pH to make it more acidic. But if we added it to a buffered solution, well, there's a good amount of a weak base hanging around. I throw in the strong acid. It neutralizes. The acid is strong, so it's pulling everything to the product side. So it's saying it's a very high K for this reaction, right? We're not looking at Ka or Kb. This is it's a reaction. It's neutralization. So it's just saying products are heavily favored here. So we've gone from a weak base mixed with a strong acid. When the reaction is over, again, we have pure water, which doesn't affect the pH, and we've converted effectively that strong acid into a weak acid. So yeah, the pH has changed a little bit now, but it's resisting that change in pH, and that's what buffers do. Long story short, effectively they turn strong bases into weak bases, and they turn strong acids into weak acids. What does that look like if we look at kind of like a bar graph type thing? So our original buffered solution is in the center. So we've got a good amount of weak acid with roughly the same amount of conjugate base. If I add a small amount of acid, well, it's going to convert some of it into a weak acid. So if we're looking at acid in total, yeah, my amount of weak acid goes up, but by a small amount. If I took that same buffered solution and added a strong base to it, some of it gets converted into that weak base. So yeah, I see it go up a little, but you're getting these small changes in pH rather than massive swings in pH if you didn't have the buffer. So this will be the last thing that we talk about, which is the Henderson-Hasselbalch equation. And what we're going to do effectively with this equation is just a rearrangement of the Ka expression. So I realize this slide's a little bit busy, so why don't I walk you through it? Again, what we have on the top, all it is that acetic acid dissociating in water. We have our buffered solution. Again, we'll just assume we have a good amount of weak acid and we got a good amount of conjugate base. What I showed here is we're making it generic again, right? Instead of being specific, let's make it really generic. I got a weak acid, it's dissociating into water, it forms hydronium, and its conjugate base. If I wrote out the Ka for that generic expression, we've seen this already in chapter 16. Products over reactants, we omit water because it's a pure liquid from the K expression. And then all I did was algebraically rearrange the equation so that hydronium is by itself. So I multiplied both sides by the concentration of acid and divided both sides by the concentration of base, and therefore I'm left with that expression you see on the right. We're going to keep moving forward with this expression. Again, it's just a rearrangement of Ka. So I could stop there, but we're going to find a more convenient way of using this expression is applying the natural log to both sides. Oops, what's it doing? My God, it's all over the place. There we go. We applied the natural log to both sides. So there's essentially our P that we're applying to the left-hand side of the equation. And then we're applying negative log to the right-hand side of the equation. It looks a little weird, but when you apply the log rules to things that are multiplied like this, what you do is once you apply the log, right, it changes it from multiplication and division to addition and subtraction. So that's why you're seeing there is this subtraction here. Don't worry about it too much. This is not a math class. I'm not expecting you to remember your log rules, though it's good to get that practice, right? So we're applying the natural log to the negative log, sorry, not the natural log, the negative log to both sides of the equation. Well, I know that negative log concentration of hydronium is pH. The negative log of Ka is just pKa. And then here's one last step. And these comes with log rules. If you flip the denominator and the numerator inside a log, it flips the sign on the outside of the log. So again, it's probably reaching back into high school to remember your log rules. Trust me on that one, but it's probably good for a good refresher. And we end with the Henderson-Hasselbalch equation. What this is going to tell us, and we're going to deal with this, we're going to keep readdressing a lot of the things that we just introduced here as we go through the rest of the chapter. So if the common ion effect is throwing you off, we're going to see it again. Henderson-Hasselbalch equation, we're going to use it in the next step, but we're also going to see how this comes into play at other places during the rest of the chapter and the rest of our lectures. So why don't we take this derived equation and we'll start to use it. So let's take this equation. It says, what ratio of weak acid and its weak conjugate base results in the pH of a solution equal to the pKa of the weak acid? So that's really weirdly phrased, and I did that on purpose. Not weirdly phrased, but there's no numbers, right? So let's take a look. Let me switch there we go. We know the Henderson-Hasselbalch equation is pH equals pKa plus the log, and it's the ratio, and that's going to use B for base and A for acid, right? So again, it's asking me what ratio of weak acid and base, so that's my ratio here, right, results in the pH of a solution where these two numbers are equal. So this might be a little bit, critical thinking required, but if you think about it, if I can get this part of the equation to equal the number 0, I could simplify that equation down to pH equals pKa plus 0, which pH equals pKa. The only reason I'm bringing this up now is you're going to do this in some of your labs, and I know that you're doing it online, so it makes it more difficult. I want you to see this early, is why we're doing that. So let me put that back up, right? We're using the Henderson-Hasselbalch equation, base over acid. And I said if I can get log B over A to equal 0, then I've satisfied that, that part of the equation, right? So if I do this, I can exponentiate both sides. So that means 10 raised to the, that will get rid of my log. So it's telling me the ratio of base to acid equals 10 to the 0th power, and anything raised to the 0th power is 1. When the concentration of the conjugate base equals the concentration of the acid, so it means they're in equal amounts, the pH will equal the pKa. Why? Because let's make up a number. Maybe the concentration of B equals 0.10, and the concentration of A is also 0.10, right? If I do 0.10 divided by 0.10, well, there's my number 1. My ratio is 1. If I dump that into my Henderson-Hasselbalch equation, the pH will then equal the pKa of that weak acid. It seems like why would we do that? It seems kind of dumb. It's kind of like a cool math trick or whatever. We're going to find out that's actually kind of important, and it helps understand why you can't use the same buffer for every kind of any kind of experiment. If we're trying to make a buffer, and we'll talk about this later, this is more just foreshadowing. The pH that buffer can buffer is only going to be roughly around the pKa. It's going to be plus and minus 1 pH unit. So imagine the pKa equaled, 6.8. That means that buffer is only good between 5.8 to 7.8 in terms of pH. So I think we're getting ahead on our skis here, but I'm just trying to foreshadow this. So buffers don't work in any combination. They actually have a very limited range in which they will work. And so that range happens to be centered directly on the pKa, and that helps you make decisions in the lab. So it's a cool math trick, but it's also very relevant. And again, we're going to bring this up in the future again. So that's why I'm trying to choose these parts first, because we're going to find out when we do titrations, a lot of these concepts are going to come up. So instead of introducing them in the middle of things, why don't we do it first, and then we'll readdress things as we go through the chapter. So this will be our last problem. So it's saying we're making a 30 millimolar solution of potassium phosphate, specifically at a pH of 7.2, which is roughly around, I think, blood pH is either 7.2 or 7.4, I forget, right? So it says I'm combining 10 millimolar of, and I'm using the term here because this is a very common way it is called the compound in biology and biochemistry, is potassium, oh, I missed a phrase. It should be potassium phosphate monobasic. It's a weird phrasing, but monobasic, it only has one. Well, we're not going to get into that. Don't worry about it. Just know the name. 10 millimolar potassium phosphate monobasic. Just know that it's the weak acid. We're also combining it with 20 millimolar of potassium phosphate dibasic. Again, don't worry about the name too much. It's just a common buffer used in biology and biochemistry. Just know that the dibasic is the weak conjugate base of potassium monobasic, of potassium phosphate monobasic. That was a lot, but again, work through this slowly. It's not that bad if you can get through the terminology. It's asking from this information, calculate the pKa of potassium phosphate monobasic, or effectively it's asking me the pKa of the weak acid. So what am I given, right? I know I have to have a pH that's equal to 7.20. The concentration of my weak acid is equal to 10 millimolar, right? I got that from up here. The concentration of my weak base is 20 millimolar. This is additional information up here. It's just saying that, yeah, the total concentration of potassium phosphate is 30 millimolar. Well, how did I get that? 10 millimolar comes from the monobasic and 20 comes from the dibasic. So more of trying to give a real world example. That's only the quantitative information I've been given. And then I'm being asked to find the pKa of the acid. So we know we're dealing with the Henderson-Hasselbalch equation. So let's write that down. pH equals pKa plus the log of the ratio of concentration of base over acid. Take a look at what I know. I have the pH. I got the concentration of the conjugate base. I have a concentration of the acid. I'm being asked to find pKa. It becomes plug and chug at this point. So let's plug in our numbers. We have 7.2 equals pKa plus the log, and the ratio is going to be 20 over 10. The nice thing is, you'll notice because it's a ratio, it really doesn't matter what your units are. As long as they're the same, they will cancel out. Let me draw that out explicitly. So 20 millimolar, 10 millimolar, right? That's where that cancels out. So if I take the log of 2, so log 2 is this number. So I have pKa plus 0.301. Therefore, pKa equals 7.2 minus 0.301. And I get 6.90 with significant figures. With two significant figures. The reason why we have two significant figures, right? We're dealing with a log, and I started with, I do have two sig fig here, 2, so my final answer should have 2. So that's kind of two representative examples of how to use the Henderson-Hasselbalch equation. Usually it's pretty obvious when you're using it because you'll be given the concentration of the conjugate base in the acid, or you'll have some combination of pH and pKa or something like that. All right, so that's the end of this lecture. It went a little bit longer than I thought it would, but that's all right. I will see you all on Monday.